In this chapter, we're going to examine more of the idea of experiments versus the idea of observational studies. Now, once again, to compare an experiment versus an observational study, your goal is to still gain information about something, but you're trying to discover a relationship between your explanatory and response. However, with an experiment, you are trying to look for a cause and effect situation. You're deliberately imposing a certain treatment or changing something to try to affect the results. Where with an observational study, all you're doing is you're observing. You're not trying to affect how the results. And so for an observational study, you're only looking for an association between variables instead of a cause and effect. So why not always use an experiment? Well, sometimes it's unethical or impossible when you're dealing with people to assign a particular treatment to someone. Some things you can't go ahead and change. You can't go ahead and change gender. You can't go ahead and change handedness. And so then you're just looking at those people and saying, okay, based on that, what can we conclude in observing stuff? Now, individuals in an experiment are experimental units. If you're dealing with humans, they're called subjects. Explanatory variables are the factors. Now, our treatment is any specific experimental condition that we are imposing on our subjects. Now, you could have several different levels of treatment, and they are all going to be affecting your factors. If you're given two different doses, you have two different levels, but only one factor. Something is statistically significant, and we'll be talking a lot about that in the last few chapters that we'll be covering. Something is considered statistically significant if it is larger than you would expect to be done by chance variation. Considering the idea of this study right here, our subjects would be all our patients, all 300 patients. Our factors slash treatments are listed here, and our response variable is our episodes of pain. Now, you might think, well, we identify our subjects, we impose our treatment, and we measure our response. Well, if you're in a laboratory setting, that often works okay. But a very simple design like this often falls short because when you're dealing with human beings, you can't just necessarily lock a human being up in a lab and do an experiment on them or a group of human beings. And so you need to account for many different other um, factors that influence human beings as they're out and about. And so you got to have a more complicated looking design, typically, unless you're in a laboratory dealing with like rats or something like that. When you're dealing with experimental design, you want to control for lurking variables. You want to have randomization occurring. And you need to deal with replication. So let's take a look through this one. As you read through this one here, what are the individuals? Your individuals are the 22 subjects that you were involved in your experiment. Same situation, but now we're wondering how did they incorporate control and comparison? Well, they did that by going ahead and giving each subject a floral scented or unscented mask. When you're dealing with an experiment, you want to compare it to something. So you need to have something to compare it to. So you'll often have a control group in which no treatment was given to you, or you will have a placebo group in which they were given like a sugar pill or some type of a fake treatment in which people think they were being given something when in reality they weren't given anything that would affect them. And then you would compare to either your control group or your placebo group to see if something happened. Now, a couple of things about the placebo. Sorry about that. Your placebo effect. Now, your placebo effect is not fully understood, but it could be affecting results by up to 35% of all the patients. As in, the patients think they're getting a treatment to help their illness, and so therefore they think they are better, or they convince themselves that they are better and their blood pressure decreases or something along that lines. Now, one of the famous ideas of placebo effects is when a kid gets hurt and you give them a hug or blow them a kiss or something like that to try to help calm them down. And while once kids get old enough, they realize that that doesn't really do anything. And that would be an example of a placebo effect. Fisher is really the founder of our controlled experiments. When he first started looking at studies, he realized that you can't really draw any conclusions from some of these studies because they were not doing a lot of controlling. There are too many uncontrolled factors, and if you want to go ahead and research them more, you may. But he's kind of the founder of all this. Now, instead of comparing results from one year to another year of farming, he says you can't do that because one year might be cloudier or wetter than another year. One year might be drier than another year, so you can't really compare. So he's like, you got to take a field, separate it into different plots, and randomly assign those plots and compare your results from each of the like-colored plots to the other color, all within the same year, to try to eliminate the variability. A completely randomized design for two treatments, you would have a simple random sample. You would randomly assign one group a treatment. You would assign a second group a second treatment. You would get your results and you would compare the results between the two treatments. Or that could even be done if you had three treatments. So you'd separate them into three groups. You'd have your three different treatments and then compare the results of all three. But they're randomly assigned. Now, we need to go ahead and try to eliminate bias when we're dealing with our sampling. By randomly assigning an individual, you are helping eliminate some of the bias. Now, double-blind experiments are also commonly used. That's where the people in the study don't know if they're receiving the treatment or a placebo, and the people conducting the survey or the experiment and collecting the data don't know who is receiving the drugs and who is not receiving the drugs. That's considered a double-blind experiment. I've also heard of triple-blind experiments, which includes the double-blind, but it also takes it to another level. It's where the statistician doesn't know which group is receiving treatment and which one is not, because sometimes a statistician can influence how the results are portrayed. You also want to go ahead and replicate your experiment. You want to do it over and over several times so that you end up getting good, consistent results, hopefully eliminating any bias. Now, sometimes you can have a simple random sample, even a large simple random sample, but you end up having a lack of realism in your situation. Now, consider this. Would looking at eating red meat and the cholesterol levels of middle-aged men really be a realistic way to study the cholesterol levels of heart disease or the effects of heart disease among all human beings? No, because middle-aged men is really only a small specific subgroup of the overall population. You would want to consider older men, younger men, and also middle-aged women, older women, and younger women. If you're looking at the effects of hairspray, yes, you could put hairspray on rats and look at the effects, but is that going to really be telling you what's going on with big-haired women who like to use lots of hairspray? That is not either. Also, if you have a situation where you have a cancer treatment which is 100% effective because they eliminate all the blood supply to a tumor, that sounds great, but it's not realistic. Considering some tumors that show up in a brain, they're kind of like spiders and reach out in all areas, and there's no easy way to cut off the blood circulation to all the tumor. So that's not realistic. So, randomly designed experiments. You randomly assign two groups. You randomly assign the treatment to one of the groups and then the other treatment to the other group, and then you compare the results. In this case, we're going ahead and we're comparing the results of two different diets on the effects and looking at weight gain. And obviously this one down here gained more weight than the one next to it. Sometimes the results are not as obvious, and then you would want to go ahead and do different statistical analysis, which we'll touch on in the next few chapters. You also want to consider matched pairs. Matched pairs are pretty much where subjects are closely related. Could be the same sex, height, weight, age, and race. Or it could be looking at twins, where one twin is assigned something and another twin is not. Or it could be a matched pair where you're looking at a before and after situation, but still only with one person. So if you're looking at the effects of tooth decay with different toothpaste, you could use one person as they're using toothpaste A, look at their results after a couple of months, and then have them switch over to toothpaste brand B, and then compare the results after that. And that would be a match pair situation where you're dealing with one person. We also have blocking. With blocking, you're not randomly assigning subjects to one group or another group. You're assigning subjects based on certain characteristics. So in other words, this kind of matches up with the stratified stuff from the prior chapter. You're breaking people into groups. So here we would break our subjects into groups by gender. Then within each gender, you would randomly assign them to a different group to receive a different treatment. And down here, you would randomly assign your women to one of three groups to receive treatment. And then you would compare the results of the men to the women. The subjects are not randomly assigned when you're dealing with blocks. But once they are within that block, they can be randomly assigned. So as we look here, we're looking at men and women, 28 men, 24 women, and their resting pulse. We have one factor, and we have two levels, male and female. It's stratified or broken up in a block design by the gender. Down below, we're looking at the dairy cows. We have a simple random sample of 60 cows, but it's really a matched pair design. You're looking at what's going on beforehand in collecting your data, and then you're looking at what goes on afterwards in collecting the data from that and comparing the results.